For decades, we have gazed at the night sky and asked ourselves, just how vast is the universe? And what secrets lie hidden within its darkness? Now, that veil is slowly lifting, clearer than ever before. Enter the Vera Rubin Observatory, the so-called all-seeing eye of the 21st century. Unlike Hubble or James Webb, which focus on a single patch of sky, Rubin scans the entire celestial sphere in just a few days, peering deep, wide, and fast like no telescope has ever done before. This is a historic leap for astronomy. Within its first 10 hours of testing, it discovered over 2,000 asteroids, including objects approaching Earth. It spotted dozens of cosmic lighthouses, RR Lyra stars used to measure distances across the universe, and then the image known as cosmic treasure emerged, revealing 10 million galaxies in a single frame. The astonishing part? That is only 0.05% of what Rubin is expected to uncover. Equipped with a colossal 3.2 gigapixel camera and a nightly data stream of 20 terabytes, Rubin does more than capture images. It records history. This is the opening chapter in our journey to decode the rest of the universe. A place where darkness is no longer a mystery, but an invitation to explore. The journey to bring Rubin to life was bound by the most extreme physical challenges on Earth, where engineering had to confront the raw power of nature. The chosen location was the summit of Cerro Pachon in the Chilean Andes, a site standing at 2692 meters above sea level. This region is an astronomer's paradise. Its high altitude reduces atmospheric turbulence. The air is exceptionally thin and dry, with minimal water vapor interfering with infrared observation, and the number of clear, cloudless nights is among the best in the world. Yet, these ideal conditions created monumental logistical challenges. Constructing atop a steep, narrow, and winding mountain made transporting massive components extremely challenging. Huge components like mirrors and cameras had to be transported by specialized trucks, sometimes moving at a snail's pace, costing millions of dollars and taking weeks to reach the summit. Engineers and workers had to operate in low oxygen conditions with frequent high winds, strictly following safety and medical protocols, further increasing the complexity and cost of the project. To ensure Rubin could scan the entire sky in just 3 to 4 nights, engineers had to solve the problem of rapid, precise motion. The high-speed, fast optics system and mechanical mount were designed to move quickly, rotate 180 degrees, and stop with pinpoint accuracy within seconds, ready to capture the next target. This speed was critical, turning Rubin into a race-against-time astronomical machine. Finally, to protect the delicate, expensive equipment from the Andes' sudden weather swings, shifting from clear skies to snowstorms in moments. The protective dome could not be traditional. It was designed as a dynamic geometric dome, capable of opening and closing in under a minute. All these factors combined, transforming Rubin into a perfect fusion of immense physical scale and near-perfect technological precision. if building the Vera Rubin Telescope was a decades-long battle against gravity and the harsh terrain of the Andes, then its operational performance is an instant declaration of speed and efficiency, officially ushering in the era of real-time astronomy. Even during preliminary testing nights, with just 10 hours of observation, Rubin produced a volume of work and discoveries that traditional survey projects would take years to achieve. Rubin's core mission isn't just about taking images, it's about generating big data on the universe's ongoing changes. With every 15-second exposure, its gigapixel camera creates massive image files, presenting an unprecedented big data challenge. During full operation, Rubin is expected to collect and process over 20 terabytes of raw data per night. Algorithms must filter, compare, and classify this information almost instantaneously. Rubin's true power lies in comparing images of the same region taken minutes or hours apart to detect changes. That is, to capture transient events in the fleeting sky. Its combination of wide field of view and continuous capture speed allows Rubin to quickly track moving objects or variations in brightness across the cosmos. In just 10 hours of testing, impressive results were already evident, confirming Rubin's groundbreaking capability. For planetary defense, it detected 2,104 new asteroids, including 7 near-Earth objects. This instantly transformed Rubin into a real-time space surveillance tool, supplying the orbital data necessary for scientists to predict and warn of potential collisions with Earth, effectively serving as the ultimate early-time shield. Simultaneously, for galactic mapping, Rubin identified 46 RR Lyrae stars. These variable stars act as cosmic lighthouses, allowing astronomers to measure precise distances and construct detailed 3D maps of the Milky Way. More importantly, they help outline the boundaries and structure of the galactic halo, the region thought to harbor most of the dark matter. These numbers are the clearest evidence of Rubin's ability to capture the fleeting sky. It doesn't merely photograph static galaxies, it hunts for events. At full capacity, Rubin is expected to generate 10 million new event alerts per night, from supernovae, variable quasars, to exotic new astrophysical phenomena. The speed of response is remarkable. This data must be processed and communicated to the global astronomy community within 60 seconds of capture. In short, Rubin's test night was not a display of beautiful images. It was the debut of a machine of time and speed. It heralds a new era where science no longer merely records what has already occurred, but keeps pace with what is happening in the hidden darkness of the universe. The release of the first test images from the Vera Rubin Telescope immediately redefined the scale and depth of astronomical surveys. At the heart of this attention-grabbing achievement is the massive mosaic image, affectionately named by scientists as the cosmic treasure. Even as an initial trial, this image served as clear evidence of the unprecedented combination of wide-field vision and the instrument's fine detail capture capabilities. In a single shot, the cosmic treasure covered an astonishing 25 square degrees of sky, a field of view many times larger than any previous telescope. And within that expanse, it captured approximately 10 million galaxies. Remarkably, this staggering count represents only 0.05% of Rubin's ultimate goal. The Legacy Survey of Space-Time aims to catalog 20 billion celestial objects over a decade. This expected data scale confirms that Rubin is not merely an observational tool. It is a cosmic data-generating machine, opening pathways to explore dark energy and dark matter in ways previously impossible. The depth of the image lies not only in the sheer number of objects, but also in the way its colors reveal the history and distances of the celestial bodies. Scientists analyze the image using spectral effects. The bright blue regions correspond to light from young, hot, luminous O and B-type stars, indicating galaxies in peak star formation stages and relatively nearby. In contrast, the deep red and faint streaks provide compelling evidence of the cosmological redshift as light travels from the most distant galaxies toward Earth. The universe's continuous expansion stretches the wavelengths, shifting originally blue light toward the red end of the spectrum. These red streaks represent galaxies from billions of years ago, offering a direct and profound glimpse into the early universe, allowing cosmologists to test models of large-scale cosmic structure evolution. Particularly striking are the faint stellar bridges, the tidal tails connecting galaxies. These are unmistakable signatures of ongoing mergers and gravitational interactions, revealing how massive galaxies grow by assimilating smaller ones and how galaxy clusters form the largest cosmic structures. Rubin's most remarkable technical achievement is maintaining ultra-high resolution across this enormous field of view. The image enables viewers to perform a dramatic zoom, starting from a panoramic view of a colossal structure such as the Virgo cluster, gradually narrowing to individual galaxies, and finally resolving details down to 0.2 arcseconds per pixel. This absolute resolution represents a quantum leap beyond the capabilities of most ground-based telescopes. At 0.2 arcseconds, scientists can not only see galaxies, but also analyze their internal structures at vast distances, distinguishing individual globular clusters, obscured star-forming regions, and intricate galactic morphology. The simultaneous capture of both macroscopic mass distribution and microscopic internal galactic physics with perfect consistency is the key that allows Rubin to open the door to entirely new frontiers in cosmic science. The success of the Vera Rubin Telescope is not only due to its sheer scale, but also lies in the integration of advanced optical, electronic, and electronic and data processing technologies, making it an unprecedented astronomical physics machine. At the heart of the system is the 3.2 gigapixel camera, a feat of engineering and the largest digital camera ever built for astronomy. This camera houses 189 deeply cooled CCD sensors to minimize noise, operating in unison to provide a 10 square degree field of view. To put this in perspective, that field of view can cover an area roughly 45 times the apparent size of the full moon as seen from Earth. Even more impressively, its resolution is held at an ultra-sharp 0.2 arcseconds per pixel. This combination of extreme wide-angle coverage and high resolution is key to Rubin's ability to repeatedly survey the entire southern sky in just a few nights. To read light and decode the history of galaxies, the camera is equipped with a system of 6 optical filters, U, G, R, I, Z, and Y. Finally, the project's greatest challenge lies in handling the enormous data flow it generates. With continuous scanning and imaging, Rubin is expected to produce roughly 20 terabytes of raw data per night, an amount that would take a typical user decades to generate. To process this volume, a dedicated data transmission network has been established. The data is compressed and transmitted at an astonishing 100 gigabits per second from Cerro Pachon Observatory in Chile across the Atlantic Ocean to the main data processing center in Miami. This near instantaneous transfer and processing capability is essential for enabling scientists to quickly detect transient events such as supernovae and near-Earth asteroids and to issue alerts to the global astronomy community within just 60 seconds of observation, turning Rubin into a cosmic time camera and an early mating system for the universe. The greatest impact of the Vera Rubin Telescope lies in its sheer speed at surveying the universe. Rubin was designed to carry out the legacy survey of space and time at a performance hundreds of times faster than previous survey projects. Whereas earlier, foundational surveys like the Sloan Digital Sky Survey took nearly 2 decades to map a substantial portion of the northern sky in detail. Rubin can map the entire southern sky with greater depth and resolution in just 3 to 4 days. This capability transforms cosmic exploration from a series of static observations into a real-time, science fiction-like cinematic experience. This dramatic increase in speed comes from a combination of technical innovations, most notably the fast optical mechanical system. The telescope not only has an exceptionally wide field of view thanks to its unique mirror design, but it can also move and stabilize with extreme speed between exposures. The sophisticated mechanical design and control system allow Rubin to shift and lock onto the next target within seconds. Critically, the entire system incorporates advanced vibration damping technology, ensuring that even during rapid movement, the precision and sharpness of images are maintained at 0.2 arcseconds per pixel. This allows Rubin to operate in a continuous loop, imaging, reading data, moving, and imaging again, maximizing actual scientific observing time. To put this astonishing performance into perspective, consider a simple visual comparison. Regions of the sky that previous surveys required months or even years to accumulate enough light and detail can be captured by Rubin in mere minutes of observation. Over the telescope's projected 10-year operational lifetime, It will image the entire southern sky approximately 825 times. These repeated observations are not mere duplication. They create a dynamic film of the universe. Each revisit enables scientists to rapidly detect newly exploded supernovae, transient celestial collisions, or fleeting gamma-ray bursts. It allows precise tracking of potentially hazardous asteroids, Kuiper belt objects, and the subtle variations in light from billions of galaxies and variable stars, providing critical data on stellar interiors and the expansion of the cosmos. Thanks to this unprecedented speed and scale, the Vera Rubin Telescope has surpassed the role of a conventional observatory to become a dynamic, four-dimensional window into the universe. It paves the way for unforeseen discoveries about the ever-changing nature of all matter, giving humanity a cinematic view of the cosmos in motion. The core mission and scientific goal of the Vera Rubin Telescope are defined by the legacy survey of space and time. This is not merely an observational project. It is a decade-long scientific commitment to catalog everything in the sky that can change. Operating at the remarkable speed and scale previously discussed. The system scans the entire southern sky repeatedly within just 3 to 4 days. By imaging the same region hundreds of times over 10 years. The LSST effectively produces a colossal and unparalleled time-lapse movie of the universe. This 10-year cinematic endeavor is more than a series of stunning images. It is a powerful scientific instrument, allowing researchers to track the evolution of celestial objects. From fast-moving dwarf planets within the solar system to the explosive birth and eventual fading of supernovae in distant galaxies. It is a grand cosmic stopwatch, enabling us to witness physical processes that until now, would have taken millions of years to observe. Over its decade-long operation. The LSST is expected to amass an enormous data trove of up to 500 petabytes. To put that in perspective, 500 PB is equivalent to 500,000 1-terabyte hard drives or the combined data storage of every academic library in the United States. This treasure trove will contain detailed information on billions of objects, including 6 million newly discovered solar system bodies and 20 billion galaxies. While recording trillions of individual measurements of their positions, brightness, and color over time. Remarkably, this data trove is built on the philosophy of open science. All raw data and process catalogs will be made freely and immediately available to the global scientific community. Breaking down barriers of geography and financial resources. Furthermore, it actively promotes citizen science. Allowing anyone with an internet connection to access. Explore and analyze the cosmic images. This approach accelerates discovery through collective intelligence while democratizing astronomy. Giving amateurs the opportunity to make groundbreaking scientific contributions. In short, the LSST mission of the Rubin Telescope is the architect of the big data era in astronomy. It not only provides the most detailed map of the sky, but also creates a dynamic temporal record transforming the universe from a static canvas into a living film. Ready to reveal the mysteries of dark energy, dark matter, and the formation of galaxies. The Vera Rubin Telescope is a direct continuation of the legacy of the great scientist whose name it bears. Vera Rubin pioneered the study of galactic rotation curves in the 1970s. She uncovered an inexplicable anomaly. Stars and gas at the outskirts of galaxies rotate at nearly the same speed as objects near the center. According to Newton's law of gravity, speed should decrease with distance from the center. This groundbreaking discovery provided the strongest clue that galaxies must be embedded within an invisible, non-luminous mass. Exerting extra gravitational force. She named it dark matter. Her work transformed dark matter from a speculative idea into a central focus of modern cosmology. day. The Rubin Telescope carries forward this legacy. Aiming to measure with unprecedented precision the influence of dark matter and dark energy across the cosmos. Rubin does not attempt to see dark matter directly. Instead, it employs the technique of weak gravitational lensing. This phenomenon occurs when dark matter, through its immense gravitational pull, bends and distorts light emitted by distant galaxies. Throughout its mission. Rubin will systematically measure the motion and shape of billions of galaxies, by analyzing minute distortions in background galaxies. Scientists can invert the process to map the distribution of dark matter effectively creating a skeleton or hidden framework of the universe. This data will allow competing hypotheses about dark matter. Such as WIMPs or MON, to be tested. And, importantly, will provide the most precise constraints yet on the nature of dark energy. The mysterious force driving the accelerated expansion of the universe. To achieve these goals, Rubin relies on two core measurements: First, the 6-band photometry. Rubin's 3.2 gigapixel camera 3 is equipped with filters spanning from ultraviolet to near-infrared U, G, R, I, Z, Y, measuring a galaxy's brightness across these 6 bands allows scientists to determine its optical redshift with high precision. Redshift indicates how fast a galaxy is moving away from us due to cosmic expansion. And consequently, its distance. By combining 2D positional data on the sky with 3D distance information from redshift, Rubin will construct the largest and deepest 3-dimensional map of matter distribution in history. This map will reveal how dark matter forms the cosmic web and how dark energy has overcome gravity to shape the large-scale structure of the universe over the past 13.8 billion years. The Vera Rubin Telescope's Legacy Survey of Space and Time is the greatest open sky library ever created. Unlike traditional telescopes, Rubin was designed to democratize cosmic data. Its comprehensiveness and speed lay the foundation for a new era of collaboration in astronomy. Data from Rubin will become a central reference. connecting and enhancing the capabilities of next-generation space observatories. The Vera Rubin Telescope is like continuing the cinematic story of the universe. Offering an unprecedented view into the changes and evolution of the cosmos. Over its decade-long mission. The first images are only the beginning. This project is a global invitation. It is not merely the work of a single team of scientists. But a shared heritage of humanity. Those of us who can access this treasure trove of data are witnesses to some of the greatest discoveries about the origins and destiny of the universe. With Rubin, we are not only seeking answers, we are transforming the way we perceive our place in space and time. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.